What I have here is several different types of PLCs. Right up here on the top, right here, I have what's called a rack system. So these are individual input-output cards. There is an individual CPU, and the power supply would mount right next. I also have several different what are called brick PLCs. This one here is a Direct Logix 105, little portable brick, very affordable, easy to work with. You have an Ellen Bradley. This is a Micrologix 1000, small little PLC, all self-contained. There's a Mitsubishi PLC. Right here, this one from Mitsubishi. All these are individual bricks along with a large Ellen Bradley. Now, along with these PLCs, I'm also later on going to demonstrate several others. What I have right here is another Ellen Bradley system, little 4-slot PLC, power supply. There's an Ellen Bradley 1500, and there's a Direct Logix 105, all connected over here to these boards. We'll work with that a little bit later. Right now, just a basic introduction to the PLCs. Let's make it kind of simple. First of all, this PLC is referred to as a rack system. And why it's referred to as a rack is everything right here removes. The CPU removes, the input and output cards are removable, and inside right there in the back what we have, it was called a backplane. Okay, this little backplane right there, you can see there's not a whole lot of electronics on there. This is mainly a communication bus where the cards themselves can communicate with the CPU. So we look at some of the cards. They're going to go ahead and have, this one is going to be a input card. This input card has got 16 terminals identified from 0 to 15. Now, one of the things with PLCs is the very first terminal will always be terminal number 0. 0 is a usable number. It's an integer. So if I have 16 terminals, the terminals are numbered from 0 to 15. This side of the terminal, we have the odd numbers. This side of the terminal, the even numbers. And yet there are two common wires right here. These terminals are for commons. So I can actually separate it. One group here under one voltage, one group here under another voltage. So this common wire takes care of these terminals. This common wire takes care of these terminals. Now on the card, there's a lot of electronics on the card. The circuit is explained several times in the PowerPoint presentation. But now what we have right here is one group of electronics for every individual screw terminal. You have basically two resistors. These little devices right here are going to be full wave bridge rectifiers. These devices here in the red are optical isolation circuits, along with an individual CPU on each one of these. So these rack systems are very, how you can say, unique, complicated. They're easy to work with, easy to deal with. Sometimes you have a hard time plugging them in. Now we take this card out, input, let's go another input. Let's take out an output card. The output card right here, again, you have outputs. Odd numbers on one side, even numbers on the other side. But the difference here is you only got one voltage going in. So the one voltage takes care of all the different terminals. Now this specific card is identified right here on the top as a TRIAC card. This entire unit right here underneath this heat sink is one long IC circuit with 16 TRIACs on that one circuit board. So it's not complex, there's just a lot of different circuits, one circuit for every terminal. And again, an individual CPU on the actual cards. Now both inputs and outputs are going to have windows here, little lights here, these LEDs. These LEDs represent the screw terminals on the card. So we have screw terminal 0, LED terminal 0, screw terminal number 1, LED number 1. Screw terminal number 3, LED number 3. So these LEDs correspond to the screw terminals. If this screw terminal is energized, the LED should be on. If that LED is on, this screw terminal should be energized. So we troubleshoot by using the actual LEDs. Now, the rack systems are pretty convenient, being you can replace things very easily. The CPU right here is a little bit different. Here we have a CPU, math processor, a BIOS chip. These small chips right here are random access memory. This chip right here is what's called an EEPROM, an expandable, programmable, read-only memory. So this would be a backup copy of whatever program would be in the memories. So it's a backup contained. The CPU is going to have a battery that maintains power to the actual CPU and to the RAM. So this prevents memory loss of memory. You have indicators on the PLC, on the CPU, identifying outruns. There's run, fault, force, low battery, communications. Every CPU is going to have a different set of communication lights. But all this PLC is a cut-down computer. No different than the computers you use for work and home, except it does not have a motherboard or a keyboard, does not have a video card, does not have a hard drive. It's nothing more than a CPU and memory. And instead of turning on all the different, 65,000 colors on a video monitor, it's going to turn on a handful of inputs and outputs. That handful of inputs and outputs is going to be right over here inside of the input and output terminals. And there's no 65 million of these. So it doesn't need a high-end memory or high-speed processor. It's pretty limited in what it's going to do. So right here, rack systems are pretty common in industry and probably the most complex and most common you're going to see. Now, these little things right here in the middle called bricks, these do the same thing that the rack processor is going to do, except they cannot be expanded. If something breaks or goes bad on this, you take the whole thing off, throw it away, and put in a new one. But these are limited. You have all these different terminals. A lot of these are not used because it's just a standard box for these guys. Now, this one right here has got a total of 6 inputs from 0 to 5. So it's only using the first 5 inputs, or the first 6. Terminal 0, 1, 2, 3, 4, and 5. The outputs right here is only 4 outputs. You have pairs of contacts as identified by the drawing here. So 1, 2, 3, 4 outputs. The rest of the terminals are not used. The indicator lights identify the condition of the individual screw terminals. If this screw terminal is activated, that light will be on. Same thing with the output. If this screw terminal is activated, that light is going to be on. And again, you have basically right here the indicators for the processor. Power, run, fault, and force. And every one of the CPUs are going to have what's right here, a programming port. This can range from all different types, from telephone jacks to USB to right here these RS-235 jacks. There's all kinds of these out there. Here we have another one right here. It's going to be a Direct Logix 105. This is Automation Direct. These things are very good. They're high-end, they're very good, they're not complicated or confusing, and they're easy to work with. Right here you got a different set of numbering, Y0, Y1, all the way up to Y7. Well, on the Allen Bradleys and all the others, X is input, and I is input and O is output. On these ones, anything made outside of the US, it's a different numbering standard. Y is output, Y is output, X is input. We have X is input, Y is output. So Automation Direct, and again, those lights correspond to the individual screw terminals being used. This one right here brings power in. You bring right there the power going in. It's 85 to 260 volts AC on these terminals with a ground. You have what's called a pulse output, so this will actually send pulses. You have a standard output right there with a common and common 3 terminals, common 3 more terminals. We look at the inputs. this is kind of interesting on the inputs. Right here you got a 24 volt power source, which is unique right there for a brick processor. A lot of these don't have their own power sources. Common wire here in the middle supports these 4 terminals. Common wire in the middle supports these 4 terminals. Now common wire here supports these 2 terminals. Now the difference right here is these 3 terminals are identified as a high-speed counter input. What that means is these will count pulses. Let's say from a servo motor, count pulses from whatever you can think of up to 5,000 hertz. So that's a lot of pulses, so you can count and measure with these. Or you can use them as individual inputs and outputs. So not bad for a processor. Than I bought last time I bought 3 of these. Okay, I paid about $95 a piece for these. So yes, you can get these things cheaper than you can get the cost of a box of relays. Another PLC in use right here, this one is a Mitsubishi. It is a Mitsubishi with 8 inputs and 8 outputs. It's a different type. Now these other ones right there are general workhorse PLCs, general industry standards. Now these coming from Mitsubishi and some of the other brands from the East are more geared for high-speed operation. We get more into that later on. But we have the terminals, and the indicator lights correspond to the terminals. Terminals for power and ground coming in. Power for voltage going out. Okay, here's your output terminals. Power going in, and all these are basically pairs of contacts. So they're paired up as being contacts. So not too complicated, now it works. And again, indicator lights for every individual terminal. And right here you got lights for the CPU. Power, run, battery, air. Now the difference is if the CPU faults, these lights are going to turn on, they change colors, they blink, they flicker, they flash. And the way these things actually work and flash are the error codes. So with any PLC, regardless which brand you run into or use, if you're going to have to troubleshoot a CPU, you're going to need the paperwork, the manuals that come with the CPU, or download the PDFs. And that will give you what the error codes actually mean, because no 2 error codes are going to be the same. All makes, manufacturers, and models have different error codes. And this applies to every PLC. Now, it doesn't matter whose brand of PLC you have. There's your power, run, and CPU fault. It doesn't matter whose brand of PLC you have. All the PLCs are going to work basically the same way. All the electronic circuits internally are going to work the same. All the responses are going to be the same. All the programming is going to be the same. The difference is in the shape, the size, and the color. Well, the question is now, how many terminals do you need? If you need a lot of inputs and outputs, you go with a rack system. If you're just operating a simple air handler unit or maybe a small boiler or small equipment, a brick PLC is nice. If you need high-speed switching, then you go with the Japanese brands. But these are all workhorses, and I'm not going to put one brand in front of the other because every one of these guys do the same thing, and every one of these are going to work fine. The biggest difference now is going to be in the softwares. Some softwares are very easy to use, but they also cost a lot of money. And there's also a lot of softwares which are not so easy to use, and they cost much less money. Now, a lot of these brands will actually provide free software for their smaller brick processors. But now you get up there in the larger processors, you got to pay for the softwares. And this all depends on the manufacturers, guys. So now we move on in just a minute. How PLCs work. PLCs don't have to be complicated, but we tend to overcomplicate things just by all natural. That's how we do it. Now, PLCs themselves, how they work. Here we have a basic operational block diagram on how this PLC is going to actually work. Simple block diagram and how it works. What I have right here is you have all the inputs that are going to connect to the input terminals. You're going to have the outputs that connect to the output terminals. Okay, inputs connect to the input terminals, outputs connect to the output terminals, and in between the two terminals you have the CPU and you have the random access memory. CPU and RAM memory. Now, as the input actually closes, so if I go this input from an open switch to a closed switch, we now have a closed circuit that allows current to flow through that circuit. As that current flows through the circuit, that tells this screw terminal there's power on that terminal. That signal right there saying there's power on that terminal is sent to the CPU. The CPU monitors all the individual screw terminals. And once there's a change in that screw terminal, then the CPU reads the program from the memory. It scans the program from the memory continuously, and every time it sees a change, then it actually makes the change in the memory. And then once the change in the memory is made, the CPU follows the next instruction, which is typically to turn on the output terminal. So once the output terminal is energized, whatever is connected to the output energizes. So it's a very simple process, but it doesn't follow all the logic of standard motor control circuits. Now, here we have the screw terminals. The input terminals themselves. Power comes into one terminal, usually a common. You have a bunch of terminals. There could be usually up to 32, but the most common is 16. And you're going to have input devices attached to these terminals. Power comes in, indicator lights tell us the condition. Now, as that input terminal closes, that power source completes the circuit, allowing current to flow through that screw terminal. That terminal right there passes through the load circuit, where there's actually an optical isolation circuit in there, and sends a signal back to the CPU. Now, once that CPU gets a signal, the power turns on the inputs. Once the CPU gets the signal, it sends a signal again through the optical isolation circuit to turn on the outputs. So the block diagram explains a lot on how the PLC works. Power comes into the output terminal. Okay, that terminal could be as many as 32 terminals, usually common number is 16. Once this terminal turns on, the indicator light turns on, that terminal's on, the output, whatever's connected there, should turn on and energize. So the actual diagrams are pretty straightforward in how that works. It all starts with an input. Once the input energizes, that sends a signal through the circuit, through the CPU, turns on the output. PLC 101.